For centuries, the standard approach of science has been to understand nature by breaking it down into smaller and smaller pieces. Consider a flower. If we were to study flowers in their natural environment, their various forms and features, that makes us botanists. But in order to really understand how the flower works, how photosynthesis keeps the flower alive and allows it to grow, we have to get inside the flower. We might then study the cells that make up the flower, how the parts of the cell function, and how they are similar to cells of other living organisms. A cell biologist seeks to understand the flowers on this level. But in order to understand how the cells function, we need to understand the complex biochemistry of the cell's metabolism. And in order to understand how the flower's cells divide and reproduce, we have to understand the operations of DNA. The biochemist and the geneticist then seek to understand the flower on a deeper level. The study of organic molecules and DNA takes us down to the level of basic chemistry. How do atoms and molecules interact and combine with one another? This is the realm of the chemist. And understanding the forces at work inside atoms is the job of the physicist. Through this approach, breaking down the flower into smaller and smaller parts, and understanding how those parts function, we have built up a deep and comprehensive view of the laws of nature, from biology down to chemistry, and from chemistry down to physics. But there's a limitation with this approach. Somewhere along the way, we lost the flower. In other words, by breaking the flower down into smaller and simpler pieces, we've lost sight of the complexity that makes the flower what it is. Is there a different approach? Is there some better way to understand complex systems? Not by examining how their parts function, but by understanding how the parts come together to create something that is, in a sense, more than just the sum of its parts. Some scientists believe that order and complexity are inevitable. The study of systems as diverse as board games, computer programs, and ant colonies has revealed some remarkable features of complex systems. Rules much simpler than those of physics and chemistry can result in a great deal of complexity. Consider a board game like chess. The game is based on a simple set of rules. Even young children can learn the rules of chess well enough to play. But while the rules of chess are simple, the game is incredibly complex. It has been estimated that the total number of possible chess games is greater than the number of quarks and electrons in the entire cosmos. With only 32 pieces operating under a simple set of rules, the complexity of the chess universe is astounding. Where does the complexity of the game of chess come from? It's not the individual moves of the pieces. It's the way those pieces affect one another. The way each move depends on the previous turn. The way the possibilities multiply each time a piece is moved.